Alrighty. So let us jump into 5.1.1. So have you forgotten natural log? Natural log and differentiation. So today we're learning to differentiate with natural log. We'll be successful when we can do more derivatives, even some more complex looking ones. It'll be all good. All right. So how is natural log defined? Harkening back to how we defined it back in pre-calc and how we defined it in Algebra 2, we defined it the same way in both those classes. We defined natural log ln of x just to be log base e of x. All right, that's how we defined it. No longer. We're redefining it. We're redefining natural log to be natural log is the accumulation function of the area under 1 over t from 1 to x, as long as x is greater than 0. Why are we doing that? Because that's how the book decided to say it. That's how our book redefines natural log. And that's why our book doesn't introduce natural log till now, because of the way they define it. A lot of their definitions and ideas don't work unless they define it this way. It's not the only way to do it. It's just the way our book does it. So that's how we're redefining natural log. Again, it's the area, the accumulation function from 1 to x of 1 over t. Yeah, it is 1 over t dt, as long as x is greater than 0. Oh, let me make sure I have the chat open just in case. I'll keep it over here just in case. All right. So for your consideration. So we are not looking at natural log. Oh geez, where are all the things? All right, there it goes. We're not looking at it like this anymore. You can still think of it like that, but that's not the definition that we're going with anymore. This is the definition that we're going after. Okay, that's how we're defining natural log. And this is part of the reason, like in calculus and beyond calculus, we don't use other logs as much, because we define natural log to basically be the area under 1 over x or 1 over t from 1 to x. So fun facts. So we're going to define natural log like this. So for your consideration. So how is E defined? So in pre-calc, we looked at this a little bit. I think we got this one in. Oh yeah, we definitely got this in before we had to leave. But E is the limit as n goes to infinity of that expression. That's how we defined it in pre-calc. And that's how pretty much everybody defines the number E. It's approximately 2.718281828. So that's how it's defined. That's how most people define it. No longer. We're redefining E. E is going to be defined a different way. E is going to be the number that when I plug it into natural log, the area from 1 to E under 1 over t dt is exactly equal to 1. So yeah, so we're redefining it to be like that. So again, we're not looking at E as defined this way anymore. Again, you still can, but this is again how our book approaches it. And I want you to see like the alternate definition that I mean, really they're equivalent things. They're exactly the same. It's just, they're written differently because different people like doing things differently. Anyways, this is how we're defining E. Again, it's the number such that when you do the area from the definite integral from 1 to E of 1 over t dt, it gives you the exact area of 1. All right. And just in case you don't know who that is, there you go. The actor and the character. All righty. Those are the big things you need to know about natural log and E. But again, our title today is natural log and differentiation. So what is our derivative of natural log? Now that natural log is defined this way, which this is part of the reason we define natural log this way, and you'll see why. the derivative of natural log, if you don't remember, is 1 divided by x. And the way we had it defined, it's more difficult to understand why the derivative is what it is. Because if we try to use the definition of the derivative on natural log, things don't work out the way we want them to. And it's honestly, I haven't found an algebraic method to show that ways like it works that way. It should somehow because it's the definition of the derivative, but we don't really have a way to show that it works. But the derivative of natural log is 1 over x. And that kind of makes sense. And if you don't see why, it's from the fundamental theorem of calculus part 2, or the second fundamental theorem of calculus, depending on how Mr. Weimer talks about it. I know he and I talk about it slightly differently, but not much. So let me show you. So I'm saying it's the fundamental theorem of calculus part 2, or the second part of fundamental theorem of calculus. Let me show you why. So I have this expression. I know I'm saying natural log is defined this way, right? Well, let's take the derivative of both sides. All right. Again, d over dx, that's the verb, taking the derivative with respect to x of whatever's in brackets. I don't know what the derivative of natural log is, quote unquote. Like we do, but we don't. We don't because we're trying to show what it is. This part over here, that's the fundamental theorem of calculus. Or the fundamental theorem of calculus tells us this. Oh, that's right. I had a little animation set up. This is what the second fundamental theorem of calculus says, or the part 2, depending how you want to talk about it, is that when you take the derivative of an accumulation function, it basically replaces, it changes variables. Hey, look, I should put Navi in there. So if I combine those two ideas, the derivative of this expression, based on what we see here, should be 1 over x. And therefore, that is why the derivative of natural log is 1 over x. Boom. So that's a lot of the theory and ideas behind natural log and differentiation. Here's what it is. That's basically, we redefine natural log in E so that we can understand why the derivative is what it is. Okay. That's why we went through that process, because this, we can apply the second fundamental theorem of calculus to, boom. And we know the second fundamental theorem of calculus is true. And if you don't know that, you should go back and read the proof in 4.4. And if you don't believe it, well, tough. We proved it. It's true. It's a fact. All right. So, and here are some other things that I just want to point out. So in properties of logs are super useful. If you don't know your properties of logs, you really should. If you don't know them, they're in the book, go check them out. So those properties are useful because we can rewrite equations and expressions with natural log in it to get simpler expressions to work with. Or for that matter, take the natural log of both sides of an equation to expand a side to make it easier to do. Foreshadowing. So one quick thing before examples. Again, the quick redefinition recap. Because again, we redefined both of these to look like this. And we did that. The redefinition E really is just so that it works for us, so we understand why things work the way they do. But again, the redefinition of natural log is so that we can find the derivative of natural log. We can prove what the derivative of natural log was, which we just did. By the way, that was like what, 2-step proof? It was really quick and easy. Boom. Okay. Some examples. So I want to find the derivative of the natural log of 5x squared minus 1. All right. So I give you the opportunity to try it on your own, but we'll just do it all together real quick. This one's not too bad. Well, the derivative of natural log is 1 over x, but in this case, there's something inside. So I'm going to use chain rule. So it's going to be 1 over the inside stuff times the derivative of the inside stuff. And in theory, you could be done, but there's easy simplification to be done. Don't forget the chain rule, by the way. Forgot I put that in there. But that's our answer. This is probably the best version of the answer, because this is an easy simplification, just putting this on top, okay? Oh, I did all these yesterday and I completely forgot what I put in there. Or Saturday? I don't know, something like that. Okay, so this is pretty straightforward example, right? I have natural log, boom, just 1 over that times the derivative of that. Here's more. So we could do that same process for this one. Do 1 over that expression times the derivative of that expression. That sounds terrible. We can do it. I'm not going to, because it's a natural log. Logs, again, as I mentioned and foreshadowed, they have properties that make things a little bit easier for us to work with. One of those is division. When you're dividing things inside, oh yeah, that's looking at that, just like looking through the whole entire process, maybe get you confused screaming. But we can use natural log to, or the properties of logs to expand that out. This looks less scary now. And in fact, we can use properties of logs even further because the square root is just a 1/2 exponent. The 3 is an exponent of 3. And if properties of logs, as you should know and remember, and if you don't, go look them up, we can take exponents inside and bring them out as coefficients or as coefficients inside as exponents, but we're not going to do that as much. I can rewrite it like this. Hey, that looks a lot simpler to take the derivative of. These two now, both of these separately, this looks more like the previous example I just showed you, as does this one. So now we'll take the derivative of everything. Again, the derivative of y with respect to x is just dy dx. And again, I'm pointing out the derivative of this minus the derivative of that. So again, I know where I'm going with everything. All right. Good stuff. So doing those derivatives, I'm going to get 1/2 times 1 over x plus 1 minus 3 over 1 over x minus 3. There's not much simplification there, so you should do that and leave it like this. 1 over 2 times x plus 1. Now you can multiply out that 2. That's fine. I didn't do that because I ran out of room and I just didn't want to multiply that all the way. And then the 3 just goes up top. Could this be condensed further into a single expression? Yeah. You only really need to do that if you are working on a multiple choice problem and you don't see your answer there. You're like, well, crap. Now I have to do a little more algebra to get there. For our intents and purposes, I don't want you to try to get calculus problems wrong because of the algebra. If you're not confident with the algebra, get to this point, box it, and then keep working to see if you can get the full, like the condensed version where it's a single expression, not 2. Okay? Because then at least you know, like you got the correct thing at one point, and then you can go from there. Boom. Here's the other way, other thing we can do. Like we can take the derivative of that. It's kind of like just using quotient rule and chain rule. There's a lot of things we could do with that. We might not want to. In fact, it'd be nice if we can make it a little like less like complicated. Like it's not like we can go through the process. Like it's not that bad. But it'd be nice if we could use the properties of logs to make things more efficient and simple to go through. So we will, because that's how we're going to approach things. So what we're going to do is take the natural log of both sides. Because if you notice, all of a sudden this bad boy, if I go back, starts looking a lot like this. And look how easy the derivative of this was compared to thinking about the derivative of this. So that's our plan of attack here. So natural log, let's split it up, take out some exponents as coefficients. So now our goal So we have to find, there we go. Now we need to take a derivative with respect to x. Hey, I should have went through this one more time before we did this, but hey, we could take the derivative of this rather simply. It's not that we can't take a derivative of this, but there's less things to keep track of in this one than there was in this bad boy. Okay. So here's that expression. Now we're taking the derivative of it. So the derivative of natural log, again, is 1 over what's inside. Here's the tricky, the part to be careful of. It's 1 over y times dy dx. Because again, we're taking the derivative with respect to x, but there's a y in there. So we have to remember a little bit of implicit differentiation. And then we're going to take the derivative of this whole thing, which again, as you saw in previous things, we can take the derivative of each term separately. So here's the derivative of 1/2 natural log of 3x minus 2. Notice the times 3 because the derivative of the bottom here. And then 2 times 1 over 2x plus 3 times 2, which again is the derivative there. Let's clean that up a little bit. Right there. I could multiply that 2 out through the bottom. I just chose not to because IDK, LOL, life. Now, really, I'm trying to solve for dy dx. I need to get rid of this 1 over y. So let's multiply by y. Woo! So in a sense, we're done because we've solved for dy dx. But also, we like to explicitly solve for dy dx often. Not always, but often we do. But especially since we already know what y is equal to. Let's plug it in. This could be multiplied out and simplified into a single expression. But again, that's a bunch of algebra that you don't need to do. Okay. Boom. That's it. Again, I don't know. I got to check updates about tests and stuff. If it's going to be online or in person. If it's in person, you need to make sure you have a graphing calculator and know how to use it. If it's online, well, you pretty much just keep using whatever you're using. But make sure you have stuff. You have a graphing calculator you know how to use. It is in person now? Okay. I've literally not followed up because I'm like, well, everything changes month to month, week to week. So I was not following it. If it's in person, which is what I'm hearing, you should make sure you get a graphing calculator and make sure you know how to use it. And for doing that, again, if you have more questions, there should be a link in Schoology with a document about how to do the calculus things you need to know how to do. Also, I can teach you and show you other things as well. Okay, here you go. Here's your practice. So it's due soon. You have the rest of the hour, this time to start working on all of it. I'm going to stop recording.